Hello, welcome back. We have started discussing superconductivity and we gave a brief outline of what superconductors are, which are the materials that are superconductor. Of course, not the entire list, that is not even possible, because every other day there is a new superconductor. However, we described what superconductivity is, and we made a distinction between the two concepts, that it is not a perfect conductor, and you should not define superconductivity as just resistivity going vanishingly small. You should also include, and that is more important, Meissner effect, which is a perfect diamagnetism to define a superconductor. Now, the reason for that is actually clear, is that a Meissner state Meissner effect is part of the equilibrium property of the system, whereas a transport is always a non-equilibrium property. So, superconductor defined as an equilibrium a state, a new state in equilibrium requires this Meissner effect, perfect diamagnetism to define it. Now, I also asked you to check whether the scenario that is depicted on the left, that a perfect conductor and a superconductor are different, and because this is as you can see, in perfect conductor it is history dependent, how you cool, whether you cool 0 field or with field, it will be different. Whereas, the outcome in a superconductor, no matter how you do it, whether you field cool or 0 field cool, it is the same. I do not know if you can have tried doing it, but let us see. I will just give you an outline of how to do it, and it is, as I say, it is extremely simple. See, for example, J equal to sigma E is a standard equation that we use for superconductors for any transport. This is the current density proportional to electric field. So, I can invert this to write equal to rho J. Okay. Now, as I said, a perfect conductor is rho equal to 0. Now, in superconductor, of course, we know that the current is finite, we can have a supercurrent, and then that means that E has to be equal to 0 inside a superconductor. So, electric field cannot be sustained inside a superconductor. Now, if that is the case, then of course, we also know that curl of E from Maxwell equation is equal to minus del B del T. So, in that case, you have so C equal to 1 and all that I have chosen. So, in that case, if E is 0, then B has to be constant. B cannot be time dependent, right. So, whatever B you start with has to remain in a perfect conductor, and let us see why that is what explains this diagram. For example, see, in this diagram you had B equal to 0 inside when it was in the normal state, then you cooled below its superconducting transition temperature and bring it inside. By superconductor I mean perfect conductor. Suppose there is a perfect conductivity transition temperature, so that below that one brings it inside a magnetic field, and it will keep its magnetic field inside whatever it was. So, that is 0. So, that remains constant, and since it was 0, it is 0. So, that is what this is. Now, in here it is just the same. See, we had field when we had the system in a normal state. This perfect conductor was in a normal state at t greater than T c, and then it is in the same situation, the T is reduced and one is coming below T c, it is brought down below T c and became a perfect conductor, and you cannot change its magnetic field. So, the magnetic field, whatever it is, it remains trapped. So, that is what a the reason for this scenario in a perfect conductor, whereas in superconductor experimentally one found out in 1933 that this is the scenario. No matter how you cool, you have to be expelling the magnetic field from inside the superconductor. So, that is the way one justifies that it is not just a perfect conductor, it is more than that, it is something different, it is actually a new state. Then we discussed this upper critical field, for example, the critical field, and then of course, the lower and upper critical field in type 2 superconductor. We just mentioned that, and so the critical field goes like this. It vanishes of course at Tc, because after that it is a normal state, and at 0 temperature it is fairly high. This value is the critical field value, critical magnetic field. So, this typically goes like H 0 into 1 minus T by Tc square, and that is the behavior shown here. This for example, is type 2. Type 2 has a behavior in which there is an Hc1 and then the field starts decreasing, and there is an Hc2. After that the field is completely expelled, and that is interesting, because in this state beyond Hc1 the system is in a mixed state where magnetic fields do penetrate the superconducting material, but in a sort of vortex lattice, which will in like tubes, magnetic field passes through in tubes. Those are called vortices, and those vortices form a lattice. So, that is an extremely interesting physics, and we will discuss it towards the end. Then we just as a phenomenology, we discussed there are these two types of superconductors and their properties. So, as we said that this type 2 superconductor is the one which is mostly in use. The materials that are used as superconductor are type 2 superconductors. Okay. So, superconducting elements, for example, in the periodic table they abound. I mean, there are lots of elements which are superconductor. The red ones are in bulk at ambient pressure. The green ones, for example, at high pressure, and this is somewhat older. There are many, there are probably there, I mean, these thing changes very often. So, this just gives you a list of things that was a few years back, and for example, calcium, Sc, scandium, strontium, yttrium, all these are under high pressure, superconductor at high pressure. The other thing is this yellow one. These yellow ones are interesting in the sense that these are in modified forms. So, carbon, for example, carbon is given in yellow, which means that there is a form of carbon which is superconducting, and we know what this is. This is called the Buckminster fullerene. If you dope it, C60, basically C60. C60 is when you dope it with potassium, for example, alkali metals, they become it becomes superconductor, and C60 on the other hand, pure carbon, graphite for example, is not superconductor. So, diamond is not superconductor, at least not normally. So, I mean so diamond is a different story, we will not discuss it here, but carbon normally, as for example, as soot is not superconductor, just typical carbon is not superconductor, whereas the that is an insulator, and whereas doped C60 molecule, for example, is a superconductor. So, but diamond also under doping becomes superconductor, but that is still controversial, what is superconducting or not. So, I will not get into that. There are these the cerium and europium are also normal superconductors, and they are also superconducting when they form this heavy fermion, when they are part of a heavy fermion compound. This is a part of history, and it should be it should be told at least once, and this is the discovery nearly at just above 4 degree Kelvin in 1911. Then in nickel 10 Kelvin, niobium nitride is fairly high Tc, for example 1941. So these are alloys. So this is the first this is the alloy which has a high fairly high Tc compared to other systems, elemental systems like say mercury, nickel, lead and so on. Then of course there are the series. This is another landmark, LbCO, which is lanthanum barium copper oxide. In 1986, Mueller and Bednarz, they found out that this ceramic compound is a superconductor under doping. So, so then so La2CuO4 is antiferromagnetic insulator, whereas if you dope with barium or lead, they become superconductivity superconductors, and this superconducting transition temperature is fairly high, 30 degree Kelvin. So, and that is called a high temperature superconductor. That was the first high temperature superconductor that was discovered, and they got their Nobel Prize within a year of their discovery. And then of course, within a very short time came this there is a superconductor called YbCO. In the same year, in just a year later, that first broke the barrier of liquid nitrogen temperature. You see, the liquid nitrogen is fairly easily available, it is not very costly, and for industrial applications, if something requires liquid nitrogen, it is not difficult to obtain, it is also not very costly. So, once this material came, the barrier of liquid nitrogen temperature was broken. This is 92 degree Kelvin. This is yttrium barium copper oxide, and it is discovered by Paul Chu and his group. And then came the series of high temperature superconductors came. As I said, the mercury doped compounds are fairly high temperature, have fairly high Tc, and they are fairly high temperature superconductors, and these were the high temperature superconductors till some years back, but then of late, as I said, a group from Germany, Drozdov and company, they found superconductivity at high pressure at in hydrides, and that has now come up to about 250 degree Kelvin or near about. But that is an extremely high pressure, 140, 150, 170, 180 GPa, gigapascal. YbCO, for example, is in ambient pressure, this 92 degree Kelvin superconductor. So, thallium doped superconductors were at ambient pressure. So, for application purposes, these are more useful in the sense that if you can bring it down to using these superconductors, then the cost is much less. All you require is liquid nitrogen. So, this is a picture you will see in many places. This is basically how the so called cube plates, which is Bednarz and Muller's discovery, they changed the way we look at superconductivity, and it also dramatically changed our understanding of the theory of superconductivity. So, what it entails is that look at the way this curve progresses. Between 1910 and 1986, superconducting transition temperature in this region increased only to Nb3G, for example, is about 23 degree Kelvin, and that was the highest Tc superconductor we had till about 1986. And in 1986, this dramatic thing happened, that Bednarz and Muller discovered lanthanum barium copper oxide superconducting at 30 degrees. Before this, of course, there was a material which is BKB, barium potassium So that let me not discuss that. That is the compound which is which was high temperature superconductor, but see, this one is actually mentioned here. This is BKB and BPB, barium lead bismuth oxide and barium potassium bismuth oxide. These were also fairly high temperature superconductors, but not in the class of this LaBaCuO4. So, the reason BAPB, is useful and important is that it also shows the undoped compound shows charge density wave. So, that is a different matter. So, that is why let us not discuss it, but this high TC class, which is the basically started with cuprates, they became famous, and their superconductivity has changed our understanding of superconductivity dramatically, and also they have changed the way experiments are done. Much more precise experiments are done these days since the discovery of high TC superconductivity. The other class of superconductors that came about in around 2008 was this these are called Fe based pnictides. Pnictides are for example, this is a pnictide in the periodic table. This column nitrogen, phosphorus, arsenic, antimony, bismuth, these when you form compounds of that kind, they are called pnictides. So, for example, here is a iron based ASO. So, these are oxides, and these are basically pnictides, they are called pnictides. They became superconductor, and these are interesting because these systems were magnetic also. These are fairly complicated superconductors, and we will not discuss it, but these are also fairly high temperature, but not as high as the cuprates in this class. Okay. Then of course, once this phenomenology is at place, let us discuss the earliest understanding of superconductivity as we go along. And one of the earliest equations that that was put forward by London and London, two brothers, that tried to explain superconductivity in a phenomenological way was this London equation. So, that is what I will come to. So, let us just discuss what it did. So, their motivation was of course to explain the Meissner effect, and they started by, and then they of course knew that it is the perfect conductor is not what the story is. This is a very different beast, and because perfect conductor does not expel magnetic field if you field cool. So, this only a fraction. So, their assumption was that only a fraction of the electrons, total number of conduction electrons become superconductor. So, that so they have divided the total conduction electron density n to two parts, n normal plus n superconducting, and so the superconducting fraction is fairly less. But the advantage is that if you if both of them are carrying current and superconducting fraction has no resistance, then of course, any measurement of resistance will still give you 0, because that part will short the current. So, under this assumption, they said that the remaining part, this n, this remains normal and dissipative, but this is superconducting. So, this is called superconducting fraction. So, they flow in parallel, and so therefore, this is like two channels, and then since one channel has no resistivity, it just shorts it. So, you will find 0 resistance still. Now, you can you can calculate this starting from a simple Drude equation, right. So, that Drude equation that we wrote down is, now you write it for the superconducting fraction, and this is what you do, minus E times the electric field that is applied. Now, of course, you see that there was a term which was plus m v by t in the Drude formula, but what you have done here is that since this is superconductor, there is no current that there is no resistance there. That means that 1 by tau goes to 0, right. So, that means tau goes to infinity. So, there is no resistivity at all. So, that is what one has used here and set this term to 0. So, your equation is only this one. Okay. Now, that there is a super current in a superconductor is actually obvious from the theory of from the basic idea that that if you okay. So, let me just show you how you understand that there is a super current, but let us first go over and finish the calculation of London derivation of, not derivation, but argument that leads to London equation. Okay. So, this is where one starts from, and then of course, you can multiply v both sides by to make it minus E n s v s. This is your j n e v basically, and so multiply both sides by n e minus n e, minus comes from the electric charge. Remember that at that time this E we do not know what is value. At that time it was thought to be just E, electronic charge, but let us just keep it what it is, and so this is the charge of the carriers. So, that is what is being done here. Now, you put this in, and E is the charge of the conduction of the those which are responsible for conduction, and then you can just now take this equation then becomes dj dt equal to minus plus ns e square by m into E. Then the procedure is fairly straightforward. Use Faraday's law, which is this, and so curl E equal to 1 by C minus 1 by C del V del T, which I wrote a few minutes back, and that is the equation, and you can go ahead and take a curl on both sides of this equation, the above equation. So, if you take a curl, then you will get del T of curl J plus curl of E n s E square by m into curl E, which will give you this n s this equation, right. So, that leads to the fact that del T of curl J plus n s E square by m c into B equal to 0. Okay. So, the above equation clearly gives you a solution which tells you that this whatever is inside this bracket is time independent. Okay. So, that is all this equation tells you, and so this is a constant independent of time. So, that means any time independent B and J will give you a solution of this equation. What London did was that he took this to be equal to 1 0, minus ns E square by mc into B. So, this is what London did, and this is what London's equation is. So, in effect, out of all those solutions you choose the one which is just this. So, as an aside, we can just discuss this thing that you know this equation, the one that I have written here, del t of curl j plus ns E square B by mc equal to 0. You can actually put B equal to curl of A, which is a vector potential. A is the vector potential, and then of course curl j plus ns this thing into curl B, that will give into curl A here, you put it in here. So, you will get curl, both of them are curls. So, this is a solution, or for example, curl of this quantity is 0, right. So, that means curl of j plus ns E square by mc into A equal to 0. Okay. So, this thing, for example, again j is n v, and so you can cancel n e, and then therefore, this gives you so this is j equal to n e p by m, right. So, you put that in, then what you will get is p here, for example, plus E A by C equal to 0. Now, this P is momentum, and this P is the momentum corresponding to the super electrons, and ideally this is replaced by the average momentum, and then this equation tells you that the total average momentum is 0. So, this is the canonical momentum, and that is that being 0 was actually says that the ground state has 0 net momentum. There is no, it's and being no electric field inside, this is what was originally predicted by Felix Bloch, that this is how the ground state should be, that it should not carry any net momentum. And so, that Bloch's idea is basically consistent with London's equation. So, that is all this aside tells us, that this Bloch never published it. So, but Bloch actually mentioned that the average momentum, canonical momentum inside a superconductor should be 0 and in the ground state, and that is actually consistent with the equation that we got from London's equation. Anyway, now we can go further, and what I will do is I will show you how magnetic field decays inside a superconductor, explaining the Meissner effect starting from London's equation.